Today I'm presenting on advances in the piezoelectric behaviour of Solvate Ionic liquid, sometimes abbreviated to SILs. So before I get started, I just wanted to give a brief definition of a piezoelectric material. So just for those who are unfamiliar, a piezoelectric material is a material that releases a charge through various potential mechanisms when it is compressed from a force. So this project started with an application in structural energy storage. And structural energy storage, in its essence, is combining load bearing with energy storage in one structure, with the aim to increase efficiency and reduce the mass of the overall structure. So if you take a car with carbon fibre components, you can integrate as these components, not as an additional component, as these carbon fibre components, structural energy storage panels, and they effectively act as a multifunctional system where they obviously are load bearing and they also store energy. This is what a multifunctional structural capacitor device looks like. You have two layers of conductive carbon fibre that act as electrodes, and they are held apart by a glass fibre separator. This system is held together by bicontinuous two-phase solid polymer electrolyte. This is what the solid polymer electrolyte looks like under scanning electron microscopy. You can see within this porous network is basically where the conductive ionic liquid sits, and the porous resin that you can see there is the solid phase that acts as the mechanical phase. At a lab scale, this is what a prototype structural capacitor looks like. The matrix in the system consists of 70% ionic liquid and 30% resin. And this is looking at it from the top, and you can see the conductive carbon fibre electrodes and a glass fibre separator there in the white. So just for those who are unfamiliar with Solvate Ionic liquids, they obviously have properties consistent with the rest of ionic liquids of being thermally stable, non-flammable and conductive electrolytes. They are a three-part ionic liquid. They consist of a solid salt that is dissolved in an ether ligand. The cation in the system is chelated and solubilized by the ether ligand, and the anion in these systems is a pseudo-spectator with obviously a diffuse charge. So, Solvate Ionic liquids are modular and tunable. There are three-part systems, so you can change out the ether ligands in these systems, the cations in these systems, and the anions in these systems. In my work, I focus on the G4 tetraglyme ligand, the G3 triglyme ligand, the lithium cation, the TFSI anion, and the FSI anion. So going into this work, the lithium cation with the G3 ligand and the TFSI anion was a benchmark applied in structural capacitors in the literature. Just recapping on the research journey. So going into this, we did some diffusion NMR of the G3 and G4 ligand systems with the TFSI anion. And the key finding of this work was that the lithium can accelerate faster than the bulk system and self-diffuse at higher temperatures up to 4 times faster than the ligand and the anion. So this is how this work started. It then evolved into applying the TFSI Solvate Ionic liquids into solid polymer electrolyte systems, and we basically showed that an optimized electrolyte, the G4 TFSI system, when applied in capacitor devices, actually had an improved performance of capacitance by 23% compared to the benchmark applied in the literature, which is quite exciting. There was a bit of a side step in the process where we actually looked at whether we could recycle these solid polymer electrolytes, and one of the favourite parts of my PhD was using a NutriBullet fruit blender to blend up some solid polymer electrolyte. And the key finding of this was that we could recover 83% of the ionic liquid that was put into the system over 5 cycles on average. We had a few side steps in the journey where we applied the traditional G3 TFSI lithium Solvate Ionic liquid in a capacitor device, and then we also applied a optimized first generation Solvate Ionic liquid in a prototype structural battery with carbon fibre, which was very exciting. And we've also applied Solvate Ionic liquids as lubricants as well, and as corrosion inhibitors. And the key findings from this work was that obviously they reduced they reduced friction by about 60% and corrosion by greater than 60%. And this was confirmed through weight loss testing and electropede spectroscopy, EIS testing as well. So coming to the topic of my talk, which is piezoelectrics, we had some basically traditional ionic liquids were shown in the literature around 4 to 5 years ago as being piezoelectric. We were curious whether Solvate Ionic liquids were. Basically, we set up, we didn't really have the equipment to do D33 testing, which is piezoelectric coefficient testing. So we set up basically on the low frame instron and did it ourselves using an open circuit potential. And we showed that Solvate Ionic liquids are piezoelectric, however it is to a much lower degree than traditional ionic liquids. We then went on to apply the Solvate Ionic liquids once again with a slightly different solid polymer electrolyte system and show that the solid polymer electrolyte made from Solvate Ionic liquids, even when 3D printed, was piezoelectric, which is quite cool. Please check out our review paper that came out early last year on Solvate Ionic liquids. You'll see some of those amazing figures over there on the right. I have to give credit to one of my colleagues, John Simon, who's a whiz on Blender. We did some amazing figures in this work, and this really showed that Solvate Ionic liquids are being used for many applications that we didn't anticipate. So, for example, they're being used a lot in recovery of rare earth metals in electrodeposition, for example, which until you actually look at the bulk of literature on it, you sort of assume they're being used for, I guess, more energy storage applications rather than electro-extraction of metals. So, I finished my PhD in March, but I had the privilege of speaking at the UN back in June 2025, representing Australia there, representing Australia in Berlin at the Global Disability Summit in April 2025, and in Fiji again in October. I have various board roles that I've done throughout my PhD, so I'm a director at the Australian Federation of Disability Organisations. I serve on the board of the Royal Australian Chemical Institute, and I serve on 2 public sector boards at a Victorian level on disability policy. I'm privileged to serve as newsletter editor for the Royal Society of Chemistry's Molten Salts and Ionic Liquids discussion group, and also serve on committees for the International Ionic Chemists Network. And with all of this, I still submitted my PhD early, 2.25 years into my tenure, so it was a very busy period of time, but very rewarding. These are my acknowledgements. Thank you to my supervisors and the team. Thank you. Feel free to connect with me on LinkedIn, and any questions?
I wonder, like in powers, what functions does your materials bring to the electric powers?
Yeah, so the whole picture of multifunctional energy storage is that obviously you have your bumper of your car is not just a bumper, it is also a battery. My project is looking at not just being a battery, but actually embedding a sensor in there. So obviously, hopefully if you get into a collision, it'll tell you if your battery is damaged to a degree that it needs replacing. Hopefully it'll give you a moment of impact sensing, sort of saying the degree of impact, and through the capacitance changes, you should show long-term damage, which is really interesting in sort of a sensing application where you could embed this midway or a third way into the plies of the composite, and you could see if there's damage and to what degree that damage is impacting the composite.
Very nice. And a fruitful PhD journey.
Thank you.